In the summer of 2019, a 17-year-old named Wolftopia finished his junior year at Scarsdale High School in New York, packed a bag, and drove to NASA's Goddard Space Flight Center in Maryland for a summer internship. It was his second summer there. The year before, he'd worked on a project about habitable zones. This time, he was assigned to something different. His task was to look at data from a satellite called TESS, the Transiting Exoplanet Survey Satellite, and examine light curves that volunteers from around the world had flagged as eclipsing binaries, systems where two stars orbit each other and, from our line of sight, periodically pass in front of one another. 3 days in, Kukia noticed something. A system labelled TOY 1338 had been flagged as a binary, two stars eclipsing each other every 15 days. But in the light curve, there was an extra dip, a dimming that did not match the rhythm of the stars. The timing was wrong for an eclipse. It was something else, something passing between us and the larger star that was not the smaller star. Kukia flagged it for his mentor, a research scientist named Veselin Kostov. Kostov looked at the data, ran additional analysis, and confirmed what the teenager had suspected. The extra dip was caused by a planet, a world nearly 7 times the size of Earth, orbiting not one star but 2, a planet with 2 suns. Wolftopia, at 17, had discovered a new world. He became a co-author on the scientific paper. His brother suggested naming the planet Wolftopia. NASA, following its own naming conventions, called it TOI 1338b. And when journalists asked the inevitable question, whether you could live there, Kukia answered with the honesty of someone who understood the data. No, he said, it is too hot. But the planet he found opened a window onto one of the strangest and most beautiful categories of worlds in the universe. Planets that orbit 2 stars. Planets where the sky holds not 1 sun but 2. This is a story about that world, about the system it inhabits, and about what it would mean to stand on a place where 2 stars rise and 2 stars set, where shadows come in pairs, and where the very idea of a day depends on the complicated dance of 2 fires in the sky. Before we begin, if you enjoy these stories and would like to help the channel grow, I would be truly grateful if you took a moment to subscribe. It makes a real difference, and it helps us keep making these. TOI 1338 is a binary star system in the constellation Pictor, roughly 1,300 light-years from Earth. That distance is difficult to comprehend. Light, the fastest thing in the universe, travelling at 300,000 kilometers per second, takes 13 centuries to cross the gap. If you had set out at the speed of light the year the Roman Empire was crumbling, you would be arriving now. The system is far away. But thanks to a satellite in orbit around Earth and a teenager in Maryland, we know it is there. The system contains 2 stars. The primary is an F-type star, slightly larger and slightly hotter than our Sun, with about 113% of our Sun's mass. It is a warm, bright star, yellowish-white, the kind of star that dominates the light of the system. The secondary is a red dwarf, an M-type star with roughly 1/3 of the Sun's mass. It is cooler, dimmer, and redder. If you could see both stars side by side, the primary would appear as a brilliant white disk and the secondary as a smaller, duller, orange-red companion. The difference in brightness is enormous. The red dwarf is about 9 magnitudes fainter than the primary, which means it emits roughly 4,000 times less light. From the surface of the planet, the smaller star would be visible, but it would be a pale, ruddy presence beside its brilliant partner. The 2 stars orbit each other every 14.5 days. They are close, separated by only about 13% of the distance between Earth and the Sun. To put that in human terms, if our Sun were one of these stars, the other would be closer than Mercury. They are locked in a tight, fast waltz, each one pulling the other in a perpetual spiral, their mutual gravity binding them together in a relationship that has lasted approximately 4.5 billion years, almost exactly the age of our own solar system. Binary star systems are not exotic, they are common. Roughly half of all Sun-like stars in the Milky Way exist as part of binary or multiple star systems. Our own Sun is something of an outlier, a solitary star travelling through the galaxy without a stellar companion. Many of the brightest stars in the night sky are binaries. Sirius, the brightest star visible from Earth, has a tiny, dense white dwarf companion called Sirius B. Alpha Centauri, the nearest star system to our own, is a triple system. Two Sun-like stars orbiting each other with a distant red dwarf companion called Proxima Centauri. Binary stars form together, condensing from the same cloud of collapsing gas, two knots of density that each gather enough mass to ignite nuclear fusion. They are born together, and they spend their lives together, circling each other for billions of years in a gravitational bond that will not break until one of them dies. The two stars of TOI 1338 are not identical twins. They are more like an unmatched pair, one dominant and one subordinate. The primary contributes almost all of the system's light. The secondary, the red dwarf, is so faint that it cannot even be detected in the combined spectrum of the system. Its presence is inferred entirely from the eclipses and from the gravitational effects it has on the primary's motion. If you were an astronomer on a distant planet, observing TOI 1338 with a telescope, you might initially mistake it for a single star. Only by watching carefully, over weeks, and noticing the periodic dimming and the subtle wobble of the primary's position, would you realise that there are two stars, and then, with even more patience, that there is a planet as well. And around these two stars, caught in the combined gravitational embrace of both, orbits TOI 1338b. It is a gas giant, roughly 6.9 times the radius of Earth, placing it somewhere between Neptune and Saturn in size. Its mass is estimated at around 11 times that of Earth, which gives it a remarkably low density, lower even than water. This means it is not a rocky world. There is no surface to stand on. It is a vast envelope of gas, likely hydrogen and helium, possibly with deeper layers of compressed fluid, and, at its core, a dense kernel of heavier elements. It is a world of atmosphere, a sphere of wind and cloud and pressure, beautiful from a distance but inhospitable up close. The planet orbits the binary pair every 93 to 95 days. The irregularity is itself significant. In a single-star system, a planet's orbital period is like clockwork, the same duration every time, but TOI 1338b orbits two stars that are themselves in motion, and the gravitational field it moves through is not a simple static well. It is a shifting, pulsing landscape of forces, stronger when the planet is closer to one star, weaker when it passes between them. The result is an orbit that wobbles slightly, a year that is never quite the same length twice. The planet's distance from the system's centre of mass is about 0.46 astronomical units, placing it in a region comparable to the space between Mercury and Venus in our solar system. This proximity, combined with the luminosity of the primary star, makes the planet hot. Estimates put its temperature at roughly 700 Kelvin, or about 450 degrees Celsius. This is far too hot for liquid water, far too hot for life as we understand it, but the orbit is stable. Calculations suggest that TOI 1338b will continue circling its two stars for at least the next 10 million years. This is not a planet in danger of being flung out of its system or spiralling into one of its stars. It has found its groove, a mathematical equilibrium in the complex gravitational field of its binary hosts. Its orbit is almost exactly coplanar with the orbits of the two stars, meaning the planet, the primary star, and the secondary star all move in nearly the same flat plane, like objects on a slowly spinning table. In 2023, 4 years after Cukier's discovery, astronomers found a second planet in the system. TOI 1338c, also known as Bebop 1c, is a gas giant roughly 75 times the mass of Earth, much larger than its sibling. It was detected not by watching for transits as Cukier had done, but by measuring the subtle wobble that the planet's gravity induces in the motion of the stars. This method, called radial velocity, is older and more established than the transit method, but it is particularly challenging in binary systems because the two stars are already wobbling around each other. Disentangling the planetary wobble from the stellar dance requires extraordinary precision. The Bebop project, short for binaries escorted by orbiting planets, was designed specifically for this purpose, and it worked. The TOI 1338 system is now one of only 2 known circumbinary systems with multiple confirmed planets. A circumbinary planet is a world that orbits 2 stars instead of 1. The concept is simple to describe and staggeringly difficult to explain. For most of the history of planetary science, it was assumed that binary star systems could not host planets at all. The gravitational environment was thought to be too chaotic. 2 stars pulling in different directions would prevent the orderly accumulation of dust and rock that planetary formation requires. The protoplanetary disk, the swirling cloud of debris from which planets coalesce, would be disrupted, torn apart, rendered sterile by the competing gravitational forces. This assumption was wrong. The first confirmed circumbinary planet was discovered in 1993, orbiting a system that contained a millisecond pulsar and a white dwarf, the exotic remnants of dead stars. But the breakthrough that captured the public imagination came in 2011, when NASA's Kepler Space Telescope found Kepler-16b, a Saturn-sized world orbiting 2 living main sequence stars. The comparison to Tatooine, Luke Skywalker's homeworld in Star Wars, was immediate and irresistible. Here was a real planet with 2 suns. Science fiction had become science fact. Kepler-16b is 245 light-years from Earth in the constellation Cygnus. Its 2 stars are both smaller and cooler than our Sun, one about 2/3 the Sun's mass, the other about 1/5. They orbit each other every 41 days. The planet, about the size and mass of Saturn, circles the pair every 229 days, at a temperature of roughly -100 degrees Celsius. It is a frozen gas giant, a world of deep cold and pale light, where 2 diminished suns provide just enough illumination to cast shadows but never enough warmth to melt ice. And yet, the idea of it, a real planet with 2 real suns, captured something in the collective imagination that went far beyond the data. The double sunset is one of the most potent images in science fiction. It speaks to something deep in the human mind, the longing for strangeness, for beauty, for worlds that are not like our own, but that we can still, in some way, understand. The idea of planets around binary stars is older than the discovery. Astronomers had speculated about them for decades. Science fiction had imagined them for longer. Isaac Asimov wrote about a world with 6 suns in his 1941 short story Nightfall. The Tatooine scene in the original Star Wars film released in 1977 placed the image of a double sunset into popular culture with such force that it became a kind of shorthand for the alien, the distant, the sublime. When Kepler-16b was found 34 years later, the scientist who discovered it did not hesitate to invoke the comparison. The real universe, they seem to be saying, is at least as strange as anything we have imagined. And it is stranger still, because it is real. Since then, approximately 16 circumbinary planets have been confirmed. The number is small, not because such planets are rare, but because they are extraordinarily difficult to detect. When a planet orbits a single star, its transits, the tiny dips in starlight caused by the planet passing in front of the star, occur at regular, predictable intervals. A year on Earth is always the same length. The transit repeats like clockwork, and algorithms are very good at finding clockwork signals in noisy data. But when a planet orbits two stars, the transits are irregular. The stars are moving. The planet's path through the light of each star changes from orbit to orbit. The dips vary in depth, in duration, and in timing. Algorithms struggle with this. The human eye, it turns out, is better. This is why Wolftopia, looking at the data with his own eyes, spotted what the computers had missed. A remarkable pattern has emerged from the small sample of known circumbinary planets. Many of them orbit near the inner edge of their system's habitable zones, the region where temperatures might allow liquid water to exist on a planetary surface. None of the known circumbinary planets are rocky. They're all gas giants, too large and too hot or too cold for life as we know it. But a gas giant in the habitable zone might have moons, and a moon of the right size with the right atmosphere orbiting a gas giant in the habitable zone of a binary star system could, in theory, be a place where life takes hold. This is speculation, but it is the kind of speculation that keeps astronomers awake at night, staring at data, hoping to find the next wobble, the next dip, the next signal in the noise. Why are circumbinary planets so rare? Or rather, why do we find so few of them, given that binary star systems are astonishingly common? Roughly half of all Sun-like stars in the Milky Way are part of binary or multiple star systems. If planets can form around binaries, as the evidence now shows they can, then circumbinary worlds should number in the billions across the galaxy. Yet we have confirmed only 16. A study published in 2025 offered a striking explanation. The answer, it turns out, involves Einstein. General relativity predicts that the orbits of massive objects precess, meaning they slowly rotate over time. In a binary star system, the orbits of both the stars and any surrounding planets precess, but at different rates. Over millions of years, tidal interactions pull the two stars closer together, which changes their precession rate. At some point, the precession rate of the stars and the precession rate of the planet can synchronize, creating a resonance. When this happens, the planet's orbit becomes increasingly eccentric, stretching into a long, narrow ellipse that brings it dangerously close to one of the stars. The planet is either consumed or ejected from the system entirely. The circumbinary planets that survive this process tend to end up in wide orbits, far from the stars, where they're harder to detect by the transit method. The planets we have found may be the lucky survivors of a cosmic culling, the few that avoided the resonance trap. The rest were devoured or cast out into the darkness between the stars. Now let us do something that science rarely permits, but that the imagination demands. Let us imagine standing on a world in a system like TOI 1338. Not on the gas giant itself, which has no surface, but on a hypothetical moon, a rocky body orbiting the planet, or on a hypothetical rocky planet farther out in the system, in the habitable zone, where liquid water might pool on the surface and the temperature might allow something like life. The first thing you would notice is the sky. Two stars, close together but distinctly separate, hanging in the firmament. The larger one, the primary, would appear as a brilliant white-yellow disk, slightly larger than our Sun appears from Earth, depending on your distance. Beside it, sometimes overlapping, sometimes separated by a few apparent diameters, the secondary star, smaller, dimmer, a deep, warm orange-red, like the colour of an ember or a late autumn sunset that never fades. The two would move relative to each other, completing a slow orbit every 2 weeks. Some days they would appear almost as one, the smaller star tucked behind or beside the larger. Other days they would separate, creating two distinct sources of light in the sky. Shadows would be strange. With two light sources at slightly different positions, every object would cast two shadows, one sharp and dark, thrown by the brighter primary, one softer, fainter, tinged faintly with the colour of the secondary's reddish light. As the stars moved through their orbit, the angle between the two shadows would shift, sometimes overlapping to create a single dark line, sometimes spreading apart like a V. Walking across an open plain, you would see your own shadow split and merge and split again over the course of days, a slow, silent dance at your feet that mirrors the dance of the stars above. The light itself would have a quality unlike anything on Earth. When both stars are high in the sky, the illumination would be bright, perhaps brighter than a clear day on Earth, with a colour temperature that shifts subtly, depending on the relative positions of the two stars. When the secondary is behind the primary, hidden from view, the light would resemble ordinary sunlight. But when the secondary emerges, adding its orange-red contribution to the scene, the light would warm. Landscapes would take on a golden amber cast. White surfaces would blush faintly pink. The effect would be gentle, like the difference between noon and late afternoon on Earth, except that it would cycle not once a day but every 2 weeks as the stars complete their orbit. Sunsets would be extraordinary. On Earth, we watch one star set, and the sky passes through a familiar sequence of colours. On this world, the sequence would be more complex. If the two stars set close together, the sky would blaze with overlapping halos of white, gold, orange, and deep red, a sunset of layered fires. If they set at different times, which would happen periodically as their orbital geometry shifts, you would experience a double sunset. The primary sets first, the sky darkens to twilight, and then, for a time, only the secondary remains. The world is bathed in a dim, reddish light, not quite night, not quite day, a second dusk, and then the secondary sets too, and true darkness arrives. Eclipses would be frequent. Every 15 days, one star passes in front of the other. When the smaller, dimmer star crosses the face of the larger, the effect is subtle, like a small dark coin crossing a bright lamp. The light dims slightly, shadows sharpen, but when the larger star passes in front of the smaller, the secondary disappears entirely, and for a brief period, the system looks like an ordinary single-star sky. A person on this world might grow up knowing these eclipses as a regular feature of life, the way we know the phases of the moon. Not a rare event, but a rhythm, a heartbeat of the sky. The climate of a habitable circumbinary world would be unlike anything in human experience. On Earth, seasons are caused by the tilt of the planet's axis. On a circumbinary world, seasons would have an additional driver, the constantly changing distance between the planet and its two stars. As the stars orbit each other, the total amount of light and heat reaching the planet fluctuates. When the planet is closest to the brighter star, it receives more energy. When it swings to the far side of its orbit, with both stars at a greater distance, it receives less. The result is a kind of micro-season, a subtle warming and cooling that cycles not annually but every few weeks, layered on top of whatever axial seasons the planet might have. Research published in Nature Communications has shown that an Earth-sized, water-covered circumbinary planet in the habitable zone of a system like Kepler-35 would be surprisingly stable. The temperature fluctuations would be noticeable but not catastrophic. Cloud cover would be reduced compared to Earth, meaning clearer skies and more dramatic sunrises and sunsets. The planet would not be the desert of Tatooine. It could be an ocean world, mild and temperate, with long luminous twilights and skies of extraordinary clarity. Life on such a world, if it existed, would evolve in a light environment of constant gentle change. Photosynthesis would need to accommodate two different spectra of starlight. Circadian rhythms would need to adapt to a day-night cycle, complicated by the presence of two independent light sources. The biology of such a world would be unlike anything that has ever evolved on Earth. But biology, as we've learned again and again, is remarkably adaptable. If there is water and energy and time, life tends to find a way. Consider what timekeeping would look like on such a world. On Earth, our calendar is built around a single star. 1 year is one orbit. 1 day is one rotation. The seasons are predictable. The solstices and equinoxes returning with reassuring regularity. On a circumbinary world, time would be layered. There would be the day, determined by the planet's rotation. There would be the year, determined by the planet's orbit around the center of mass of the two stars. And there would be the stellar cycle, the 15-day period during which the two stars complete one orbit of each other, causing the light to shift, the eclipses to recur, and the microseasons to pulse. A civilization on such a world would need a calendar with 3 interlocking wheels, a clock with 3 hands. Their festivals might be timed not to the solstice, but to the moment when the two stars align, when the eclipse brings a brief, peculiar dimming of the sky, a moment of shadow that recurs every 2 weeks like a cosmic heartbeat. The night sky on such a world would have its own wonders. When both stars have set, true darkness would arrive, and the stars beyond the system would blaze with a clarity that Earth's thicker atmosphere rarely permits. But some nights would not be fully dark. If the planet orbits a gas giant like the hypothetical moon we imagined earlier, the giant would fill a significant portion of the sky, reflecting the light of 2 suns back down onto the moon's surface. These nights would be suffused with a soft reflected glow, enough to read by, enough to see the landscape in pale pastel shades. The giant's bands and storms, rendered in reflected binary starlight, would be a permanent feature of the sky, a vast and slowly churning canvas overhead, changing from hour to hour as the gas giant rotates. Plants, if they existed, would face an interesting challenge. Photosynthesis on Earth is tuned to a specific range of wavelengths, primarily red and blue light, which is why plants appear green. They reflect the green light they do not use. On a circumbinary world, the two stars emit light at different temperatures and therefore different spectra. The primary star would provide light rich in the yellow-white range. The secondary, the red dwarf, would contribute light heavily weighted toward the red and infrared. Plants might evolve pigments that absorb across a broader range of wavelengths, capturing energy from both stars. They might appear darker than terrestrial plants, absorbing more of the visible spectrum and reflecting less. A forest on such a world might be dark olive, or deep burgundy, or nearly black. The colours of life would be tuned to the colours of 2 different suns. Animals, if they existed, would need to cope with the variable light. Eyes might be more sensitive to red and infrared light to make use of the secondary star's contribution. Some animals might be most active during the brief period when both stars are above the horizon, taking advantage of maximum illumination. Others might prefer the dim reddish twilight that occurs when only the secondary star is visible, a niche that has no equivalent on Earth. Predators might time their hunts to the eclipses, those moments every 2 weeks when the light changes abruptly, and prey animals are briefly disoriented. Evolution, on a circumbinary world, would play a game with 2 sets of rules. A game that produces creatures and strategies that we can only dimly imagine. Water, too, would behave differently. Oceans, if they existed, would respond to the gravitational pull of two stars instead of one. Tides on Earth are driven primarily by the Moon, with the Sun contributing a smaller effect. On a circumbinary world with no large moon, the two stars would be the dominant tidal forces, and because they orbit each other, the tidal pattern would be complex. Every 15 days, as the stars complete their orbit, the tides would surge and recede in a rhythm quite unlike anything on Earth. Coastal life, if it existed, would need to adapt to this double tidal pulse. Intertidal zones would be wider and more dynamic. The shoreline would be a place of constant, gentle negotiation between land and water, shaped by two gravitational hearts. A civilization arising on such a world would think differently about the sky. On Earth, the sun is singular. It is the centre. Many cultures have built their religions, their calendars, and their architecture around the idea of one central fire in the sky. On a circumbinary world, duality would be built into the culture from the beginning. Two suns, two shadows, two sources of warmth. The number two might carry a significance in art, in mythology, in philosophy, that it does not carry on Earth. Balance, partnership, the interplay of opposites. These themes would emerge naturally from the daily experience of living under paired lights. A child growing up on such a world would learn from infancy that the sky is not dominated by one thing. It is a relationship, a conversation between two lights that have been circling each other since before anything alive was there to watch. Music, if it existed, might reflect the rhythms of the binary orbit. A 15-day cycle of brightening and dimming, of eclipses and separations, would provide a pulse that composers might use the way terrestrial composers use the heartbeat or the breath. Dance might follow the slow, interlocking arcs of the two stars, one dancer bright and dominant, the other smaller and more elusive, circling and eclipsing and separating in a choreography that mirrors the sky. How does a planet form around two stars? The process begins, as it does in single-star systems, with a protoplanetary disk, a vast rotating cloud of gas and dust left over from the formation of the stars themselves. But in a binary system, the disk is not a simple, smooth structure. The gravitational influence of the two stars stirs the inner region of the disk, creating a central cavity, a hole in the disk where the tidal forces of the binary prevent material from accumulating. Planets cannot form in this cavity. They must form farther out, in the calmer regions of the disk, and then migrate inward over millions of years, drifting through the disk until they reach a stable orbit near the inner edge. This is what the evidence suggests happened at TOY 1338. The alignment of the planet's orbit with the binary's orbit, measured through a subtle effect called the Rossiter-McLaughlin effect, indicates that the planet and the stars all formed from the same disk. The planet did not arrive from elsewhere. It was born in this system, coalesced from the same primordial cloud that gave birth to its two stars, and slowly spiraled inward to its current position. The process took millions of years. It required a delicate balance of forces, a Goldilocks migration that brought the planet close enough to be detectable, but not so close that it was destroyed. The fact that it exists at all is a testament to the resilience of planetary formation, to the ability of nature to build worlds even in the most gravitationally complicated environments. TESS, the satellite that made the discovery possible, is a remarkable instrument. Launched in April 2018, it is designed to survey nearly the entire sky, dividing it into sectors and monitoring each one for 27 days. Its 4 cameras photograph a given patch of sky every 30 minutes, measuring the brightness of hundreds of thousands of stars simultaneously. When a planet passes in front of a star, the brightness dips by a tiny, measurable amount. TESS records that dip. Over the course of its mission, TESS has observed more than 1 million stars and confirmed thousands of exoplanet candidates. But TESS is not equally good at finding all kinds of planets. It excels at detecting planets with short orbital periods, those that transit frequently during the 27-day observation window. A planet like TOI 1338b, with a period of 95 days, transits only once during a single sector observation. To catch it, you need luck, patience, and in this case, a teenager with sharp eyes. The software designed to find transits in test data is optimized for regular repeating signals. Circumbinary transits, with their irregular timing and variable depth, slip through the algorithms like water through a net. This is why the Planet Hunters Citizen Science Project exists. It puts the data in front of human eyes, thousands of volunteers around the world who scroll through light curves looking for anomalies. Wolftopia was examining their flags when he found his planet. The discovery was a collaboration between a space telescope, a global community of volunteers, and one attentive young person. The constellation Pictor, where TOI 1338 resides, is a faint southern hemisphere constellation that most people have never heard of. Its name is Latin for the painter, or more precisely the painter's easel. It was introduced in the 18th century by the French astronomer Nicolas Louis de Lacaille, who catalogued the southern sky from the Cape of Good Hope and named several constellations after scientific instruments and artistic tools. Pictor contains no bright stars. It is invisible from most of the northern hemisphere. It is the kind of constellation that exists mainly on star charts, a quiet corner of the sky with no mythology attached to it, no ancient stories, no guiding stars for navigators. And yet, in this unremarkable patch of sky, 1,300 light-years away, 2 stars circle each other in a 15-day waltz, and a gas giant the size of Saturn traces a wobbly orbit around them both, accompanied by a more massive companion farther out. An entire solar system, complex and dynamic, and 4.5 billion years old, going about its business in perfect indifference to whether anyone on Earth ever notices. The fact that we did notice, that a satellite in orbit, and a student in Maryland and a network of volunteers around the world came together to detect a faint irregular dimming in the light of a star too faint to see with the naked eye, is one of the quiet miracles of modern astronomy. The discovery of TOI 1338b matters not because we will ever visit it. We will not. 1,300 light-years is a distance that no current or foreseeable technology can cross in a human lifetime. It matters because it tells us something about the universe we live in. It tells us that planets form around binary stars, that the gravitational chaos of 2 suns dancing together does not prevent the slow, patient accumulation of matter into worlds, that the universe is more inventive, more generous with its planet-making than we once assumed. It tells us that the double sunset, that iconic image from science fiction, has real counterparts scattered across the galaxy. Somewhere, right now, 2 stars are setting behind the horizon of a world that has known no other sky. The light is fading in 2 colours, the shadows are merging, and the night that follows is lit, perhaps, by the glow of a gas giant filling half the sky, its bands and storms illuminated by the reflected light of 2 suns that have already set. We do not know how many circumbinary planets exist in the Milky Way, but given that nearly half of all sun-like stars are in binary systems, and given that planet formation appears to be robust even in these environments, the number could be in the billions. Most will be gas giants, like TOI 1338b. Some may be smaller, rockier, closer to habitable. A few perhaps may harbour moons with atmospheres and oceans and the conditions for life. We have no way of knowing yet. But the search continues. Tess is still watching the sky. Volunteers are still scrolling through light curves, and somewhere, perhaps, another 17-year-old is about to notice something that the algorithms missed. There is a deeper lesson in the story of circumbinary planets, one that extends beyond astronomy. For decades, we assumed these worlds could not exist. The mathematics seemed to forbid it. The gravitational chaos of two stars was thought to be incompatible with the slow, gentle process of building a planet from dust. We drew a line and said, beyond this line, planets cannot form. And then we found them. We found them exactly where we had said they could not be. This has happened again and again in the history of science. We discover a rule, we become confident in the rule, and then nature shows us an exception that forces us to revise everything. Planets cannot form around binary stars. Planets cannot exist in the habitable zone of a red dwarf. Life cannot exist in boiling water, in acidic pools, in the crushing pressure of the deep ocean. Each time the universe gently corrects us. Each time reality turns out to be stranger, richer, more creative than our theories predicted. The lesson is not that theories are useless. They are essential, but they are maps, not territories. And the territory is always larger than the map. There is something deeply human about this story. Not just the science, but the way the science happened. A teenager, a summer internship, 3 days of looking at graphs, and then a moment of recognition, a pattern that did not fit, a timing that was wrong, and the quiet, extraordinary realization that the wrongness was not an error, but a world. Wolftopia did not build the satellite. He did not design the algorithms. He did not invent the transit method. But he saw what the machines could not see. He noticed. And in noticing, he added a planet to the catalogue of known worlds, a small entry in a vast database, but also a reminder that discovery is not always the province of genius, or seniority, or expensive equipment. Sometimes it is the province of attention, of patience, of a young person sitting at a desk looking at data and thinking, that does not look right. Kukia was 17. He had just finished his junior year. He was interested in astrophysics, had been since childhood. His mother, a geologist, had passed on a love of science. He had joined his high school science Olympiad team. He had already done one summer at Goddard the year before, working on a different project. He was not a prodigy in the dramatic sense. He was a curious, diligent, observant young person who was given access to real data and took the work seriously. The planet he found did not appear because he was extraordinary. It appeared because he was attentive, because the data was available, because the tools existed, because a satellite was watching the sky, and a global community of volunteers was sorting the results. And one intern happened to look at the right light curve at the right moment and recognize that the dip did not belong. When journalists asked him what it was like to discover a planet, Kukia was modest. He credited his mentor, Veselin Kostov, for recognizing the significance of the signal and guiding the confirmation process. He acknowledged the volunteers whose work had flagged the system in the first place. He noted, with a teenager's directness, that he did not get to name the planet. His brother's suggestion, Wolftopia, did not make the cut. The planet remained TOI 1338b, a designation as impersonal as a license plate. But the story behind the name, a kid from Scarsdale who found a world with 2 suns on his 3rd day at work, has a quality that no catalogue number can contain. The software that confirmed Kukia's finding is called Eleanor, named after Eleanor Arroway, the protagonist of Carl Sagan's novel Contact. A story about a scientist who listens for signals from the stars and, against all expectation, finds one. The naming is not accidental. It is a nod to the tradition of quiet, persistent searching that defines much of astronomy. Most of the time the data is ordinary. Most of the light curves show nothing unexpected. But occasionally, in a graph that looks almost like all the others, there is a signal, a dip, a wobble, a timing that is wrong, and a world emerges from the noise. 1,300 light-years away, in a constellation most people will never see, 2 stars are circling each other tonight. One bright, one dim, one white, one red. They have been doing this for 4.5 billion years, long before anyone on Earth knew they were there. Around them, a planet the colour of storms and twilight is tracing its patient, wobbly orbit, rising and falling through the shifting gravity of 2 fires. It is a world we will never visit, a sky we will never see with our own eyes. But in the data, in the faint irregular dimming of a star too faint to see without a telescope, it is there, real, measured, known. A gas giant with no surface, orbiting 2 stars in a constellation named after a painter's easel, discovered by a 17-year-old who was paying attention, and it is not alone. Across the galaxy, in binary systems we have not yet observed, other worlds are tracing their own wobbly orbits around their own paired suns. Some are gas giants, vast and uninhabitable. Some may be smaller, rockier, wetter. Some may lie in the habitable zone, where the combined light of 2 stars warms a surface where water gathers, and chemistry does what chemistry does when given enough energy and enough time. We do not know what is out there, but we are looking. Every night the satellites watch, every day the volunteers scroll, and every so often the data shows a dip that does not fit, a signal that the algorithms missed, a world that was waiting to be found. We cannot go there. We cannot touch it. We cannot stand on its surface and look up at the 2 suns that a teenager in New York helped us see. But we know it exists, and in knowing, we have expanded the boundary of the known universe by 1 world. One more point of light that is not just a star but a place, a system, a sky with 2 suns where the shadows come in pairs and the sunsets never look the same way twice. Thank you for listening to Strindberg Space Stories. If this story gave you something to think about or something to rest to, subscribing to the channel helps us keep making them. Take care of yourself, and keep looking up.